And the presentation is... Huh? Okay. Creo que las puedes esconder. Aquí si le picas ahí more, puedes esconder el floating menu. Y ya no es que se quede ese ahí en la esquinita. Ok.
Thanks a lot for being here. We're just about to start with the physics everywhere all at once. So please, we ask you to remain quiet, both to respect our speaker, but also solve the room and hear correctly. Today we have Professor Dr. Gerardo Velázquez. Dr. Velázquez was born in Mexico City, and since an early age, he was interested in physics. He completed his undergraduate studies at the Higher College of Physics and Mathematics of the National Polytechnic Institute. Later obtained a PhD in theoretical physics from Cinvestadt in Mexico City, and he was invited Aural University of Chile, Catholic University of Temor, and the Center for Scientific Studies in Chile. Currently, he is a STEM professor at ASUCQ, teaching the classes of physics. Please give Dr. Velázquez a big round of applause, since he is local from the university.
Okay, hello everyone. Everything around you, so every phenomenon that you have around you, it has physics within. So there is no system that you can imagine where physics is not involved. However, what I'm going to try to do today is to show you that you can find physics basically in everything and everywhere. So my idea of today's talk, okay. Yeah, so what I'm going to do is I'm going to talk about this phenomena that occurs in everyday life, right? So the first phenomenon that I'm going to talk about is the Magnus effect. So you might not heard about this effect before, but I am pretty sure that if you like sports, you have seen this before, okay? Later, I'm going to talk about refraction of light. For example, here, mirages and other phenomena that you observe every day. It's basically governed by this phenomenon of refraction of light. Later, I'm going to talk about total internal reflection. It doesn't sound very cool necessarily, but we have a lot of good technology thanks to this phenomenon. And the last thing, I'm going to talk about cars in circular motion, okay? So it's basically phenomena that we observe every day, right? Okay, so it's the other way around. So generally speaking, what is the Magnus effect? The Magnus effect has to do with the motion of an object inside a fluid when this object is spinning. So basically what you will observe in that case is that the object that is moving with a certain spin, it's going to be deflected, so it's not going to follow a straight path, okay? And where can you observe this? For example, in sports like soccer, tennis, volleyball, right? So can you click in the first video? So in the first video, what you will observe is first, these guys, they're going to...
basketball over the edge. You can see that the basketball gets pushed around a bit.
So practically it falls like this, right? But now notice what happens when they spin it. That's just the funny stuff, right? But what is important here is notice what happens, what was the difference when this guy exert a spin on the ball. So what did you observe in that case? Exactly, so it start to move, not following a straight path. So it start to move and following this kind, basically a deflection from the straight line, right? Can you click the other video? So notice the spinning and notice this bend of the ball. So volleyball. Okay. And the last one is my favorite. Roberto Carlos against France. So notice the deflection of the ball, right? Okay. So notice that this effect, that it's basically pure physics, it appears in sports, right? But my intention today is to try to give you more or less an explanation of why this happens, okay? And it has to do a little bit with physics, fluid in physics. Can you? No, the next slide, because I think this thing is not working. Okay. 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 So for this, what I want to do is to talk a little bit about velocity and pressures in fluids. So I'm going to talk about the Venturi effect. So what is the Venturi effect? When you have a fluid in motion, remember that in fluids, what you have is a quantity that is called the pressure, which is basically the amount of force that you are applying per unit of area. And when you have fluids in motion, the pressure is going to be affected by the velocity at which the fluid is going through. So notice that in this case, in this experiment, what you have is a pipeline. And notice that the pipeline, it's narrow here, right? So the diameter of the pipeline here at the center is really, really small. So something that we know in physics is that for a fluid to be, for a fluid that is flowing, in order to keep the same, to keep the flux constant, basically the amount of fluid, the volume of fluid, or in this case air, that is going to pass through this region is going to be the same one that you need to pass through this region at the same time. So notice that, for example, and this is something that you have experienced when you water plants, for example, what happens if you want the water to go faster? So basically what you need to do is to close the end of the hose, and at that moment what you will observe is that the fluid is going to move faster and faster, right? And that makes sense because if you have, let's say, a meter cube of fluid flowing through this pipe, if you want the same amount to flow through this narrow pipeline, what you should observe is that the velocity that you need to have in here should be bigger, right? Because you need to move the fluid faster so you can have the same amount in this region, right? So at this moment, this guy is not blowing. Oh no, it is blowing, but so can you play the video, please? Okay, so what I want you to observe in here is the following. So before, pass it here, pass it there. Before, can you go back? Just before this guy is blowing, right? A little bit more back. Thank you, Diego. There. So what I need you to notice in here is that before he starts to blow air into the system, so notice that the fluid that you have here is basically at the same level. What is the meaning of that? That the pressure that you have in here, in this pipe, is equal to the pressure that you have in here, which is basically the atmospheric pressure. So what we have here is that before the fluid is start to move along the pipeline here, sorry, the pressure on the system is the same, right? Now, what is going to happen when this guy starts to blow in here? For example, if the pressure in this pipeline is larger than that of the atmosphere, what you will observe is that this portion of the fluid is going to sink, and this portion over here is going to go up. So that would mean that the pressure that you have here is bigger, right? And what would happen, for example, if the pressure were smaller? So if the pressure is smaller, the tube is open here, so the atmospheric pressure is going to win the battle in here, and what you will observe is that this, for example, the fluid is going to go up, right? And this one over here is going to go down. So Diego, can you play the video? So notice at the moment that this guy is blowing, can you pause it there? So notice at this moment, the guy is blowing the air. So air is flowing in this system. And notice in this case, we know that the velocity of the fluid is smaller with respect to this one. Because remember, in order to have the same amount of volume passing through this part, the velocity at this point should be larger than any other point on the system. And notice what happens in here. The velocity is smaller than in here. And what happens in here? The fluid went down. So the only explanation is that something is pushing the fluid down. That something is precisely the pressure that the air is exerting on the fluid. So notice that in this case, the pressure that I have here is larger compared to that of the atmospheric one, right? And now notice what happens here in the middle, right? So notice that here in the middle, the velocity of the fluid is larger. And what happened here with the fluid? The fluid went up. How do we explain that? That in this open part of the tube, the atmospheric pressure is bigger than the one that you have here. So notice what is the effect. The larger the velocity, right? The lower, sorry, in this case, in this part, the larger the velocity, what happens with the pressure? The pressure of the fluid decreases, right? And the smaller the velocity, as it is shown in this part, what happens with the pressure? It increases, right? So that's precisely what happens. Can you, or the next slide if you want. Okay. Okay, and then what happens in Magnus effect? So in Magnus effect, what you have is an object that is rotating. And in this case, what I am drawing is precisely the velocity of the fluid in which this object is moving through, right? And what I need you to notice is the following. In the upper part, so notice that the rotation of the object in this case is clockwise. So the object is rotating in this direction, right? And notice that this portion of the ball in this case is going to drag the air in this direction, and it's going to increase the velocity of the air on that top layer. So notice that in this case we have larger velocity than in any other point of the fluid. And remember, larger velocity means less pressure. So the pressure that we have here on the top of the ball is smaller. And now notice what happens in here. So notice that in here, the fluid is going in this direction. It's going to your right, but the spinning of the ball is in the opposite direction. So here in the lower part, the drag of the spinning object is slowing down the fluid, right? And remember, slower velocity means a higher pressure. So notice that what we have in here, it's a region where you have lower pressure, and here you have a bigger pressure, right? Because the velocity in here is smaller. And the difference in pressure that you have here, what is going to create is a lifting force precisely upwards. And that's precisely the force that is pushing the falling basketball to go in that direction. Because that's what happens, right? And that's precisely the same effect that you have, for example, in soccer. When you want to curl the soccer ball, what you need to do is to give a spin to the ball so that you can take advantage of this effect, okay? So really cool, right? Okay. So I don't know if you have any questions. And this effect, for example, it's important in the sense that, for example, you can set objects in motion. I remember that there was technology where you have cylinders in ships, and these cylinders, they were actually spinning. And using this Magnus effect, they were propelling the ship without the need of using oil, for example, right? What is the disadvantage? No air, no motion, right? And you need to adapt the spinning of the object precisely to have a direction for the motion, right? So I don't know if you have any questions here, right?
So, good question. So, just I guess in theory, would it be possible to make like a flying like an airplane, but based on this, something like that?
Yes, when this phenomenon was discovered, I don't recall what was the name of this engineer, but he invented an airplane that was based in cylinders that they were just spinning. So, but I mean, it depends a lot in the direction of the motion of the air, something that you cannot control, for example. And in the direction, you need to be careful.
So I'm guessing it would probably be a lot less efficient than
place. That's
Yes,
not light.
but something that I can tell you is that the airplanes, not because of the Magnus effect, but because of the difference in pressure, that's why airplanes fly. Because the wings of the airplane, they are designed in such a way that they generate or they create a slower velocity of the air in the lower part of the airplane and a larger velocity on the top. And again, what you're going to have is a region, which is the top of the wing, that has a smaller pressure than below. And that difference in pressure is precisely what is lifting the airplane, right? So, as I told you, physics is everywhere, guys, okay? Okay, so the next topic that I want to discuss with you guys is refraction of light. What is refraction of light? Basically, the refraction of light is the bending of light as it travels from one medium and it enters another different medium, right? And this bending of the light is produced basically because the speed of light changes from one medium to the other, okay? And here you have an example, right? So in this case, what you have is a piece of glass, and notice that it is surrounded by just air. So notice that in this part that you have here, the light is traveling on inside air, and then you have here this boundary between the two elements, and notice what happens when the light goes from the air into the glass. It follows a straight path or it is bent. It is bent in this case towards the top, right? And notice when the light again travels from the glass again into the air. So notice that here you have another bend, right? Because the straight path, it should be something around this direction, but notice that that's not the path that the light is following, right? And where can you observe this phenomenon on what it is? You use it all the time, every time, and every day. Your eyes, because notice that your eyes, they are basically some lenses. So the light that it's coming from the exterior of your surrounding, it enters your eye, and then your eye, which is basically a liquid, so it's not air. So when the light goes from the exterior into your eyes, the light is bent, and actually it is made to converge into your retina, okay? So notice that you use this phenomenon all the time, right? Okay. And where else do we find refraction? For example, in mirages. So I don't know if you have experience when you are driving, for example, in a weather that it's really, really dry and really, really hot. Sometimes what you can see is something like this, right? So apparently what you have here is kind of like water that is reflecting the cars, right? But there is no water there. So what happens is that in dry weather, the layers of air that are closer to the road, they are at a higher temperature than the ones that are at a higher altitude. And the speed of light in the air, it depends on the temperature, okay? And precisely what happens in here is that this beam of light, for example, in this cactus that is going down, as it goes down, it is changing from layer to layer to different velocities. And remember, the change in the velocity, what causes is the light to bend. So what is happening in here? The light that is coming in here following this path P, our brain, it interprets this light to be coming from this path that is down the road. So what you are observing in here is actually an image that is created by the refraction of light, okay? So that's why we have this myth that when you are in the desert, sometimes people exclaim, there is water there. No, there is no water there. What they are observing is an image that is created by refraction, right? And you can observe also this type of images, for instance, in really cold weather, because again, what you will observe is that the layers, depending on the height that you are measuring, they are different, and the light that is traversing those regions is going to undergo refraction, right? So that's why in really cold weather, sometimes you see, for example, ships or mountains that are kind of like floating from the water, but that's not floating. What you're observing is just an image of created by refraction, okay? Okay, another phenomenon that it's really interesting is this one. So what happens at dusk? So when you are looking at the sunset, and here in campus we have really cool sunsets, right? So you observe the sun. You are not looking at the sun. The sun is not there actually, okay? So what happens? Again, by refraction, the sun appears at a higher position than it actually is. So what you are observing is, again, so here you have the horizon. The sun is actually down the horizon, but again, the light coming from the sun, it travels from outer space, it enters the atmosphere, so it's changing again from one medium to another. So it undergoes refraction. And that in that light that it's bent, it's what we perceive as the image of the sun that it's on the horizon, right? But actually, it is not there, right? I have an experiment. Of course, I cannot put a sun here, right? And I cannot perform this experiment. But what I'm going to try to do is to mimic the experiment. So can you share my my screen? That one. Okay. So what I have here is precisely a cup. And if you notice, I have a coin in there, right? So it's this coin that you have there, right? So the coin is the sun. And what I'm going to do is I'm going to try to hide the sun. Okay, so notice that okay, so I think it's going to be easier if I move there, right? So notice that in this case, this portion over here, that's going to be your horizon. So notice that in this case, the medium, it's air all the time. So you do not see the coin. And what I'm going to do now is I'm going to change the medium. So what I'm going to do is I'm going to pour a little bit of water there. And what I want you to see is check what happens, okay? I did this experiment yesterday. It worked. So I hope it's going to work today, okay? Oh, it moved a little bit, but it doesn't matter, okay? Okay, so now notice what appeared in here. The coin. So that's the effect that happens with the sun, right? So the light coming from the coin, it is bent when it travels from the water into the air. And what we perceive is precisely that image that is created by refraction. So again, we apparently see the coin, but the coin is not there in that position, right? So that's what happens, for example, with the sunset, okay? Which is, again, just physics and refraction. Really cool, isn't it? So now you have a trick to show in Paris or with your little brothers, magic. Actually, it should work with other liquids. What I don't know if it's, I mean, when I was doing this experiment, I actually measured the diameter of the cup. I measured the height, and I calculated what should be the position of the coin for this to work using the index of refraction of the liquid. So if you change the liquid, you can perform the same computation. So where should I put the coin so that the experiment works? So physics works. Okay. Yes, I mean, you can use a transparent one, but you will see the coin. It depends on the position where you are looking at, because that's precisely what happens. I don't know if you have seen this experiment where you have precisely a transparent glass, and you put a pencil or something, you see that the object is bent. So again, that's because of the refraction. And this, believe it or not, it has some practical applications. For example, maybe, no. For example, if you want to fish with a spear, so usually what's the thing that an experienced fisher tells you? Do not aim at the image. Why? Because again, because of the formation of the image by refraction, the fish is not where the image is located. Okay, actually the fish is closer to you and it's deeper. So that's why they tell you, instead of aiming to the image, aim closer to you and try to hit deeper if you want to catch the fish. And the reason why, it's precisely because of this effect. Because the light coming from the fish, as it travels from the water into the air, it is bent. And remember that our eyes, what they try to do is our brain processes the image in such a way that we see the image coming from a different position than where the actual object is. And this is something that also happens, for instance, in just go back to the presentation, please. For example, when you go to an aquarium, for example, again, the fish, what you are looking at is an image of the fish. So that's why the fish appears to be closer, but actually it's at a different position, because again, what you have there is light coming from the fish, traveling into water, from water into the material of the walls, and then from there to your eyes. So you have there a bending of the light, and the fish, it's not where you apparently see it. Okay? So really cool, isn't it? Okay. What other, yes, can you, okay. So you need to, so we need to enter the presentation. Okay. Yeah, thank you. Okay, another phenomenon where you can observe refraction is precisely in rainbows. Because again, what happens in the rainbows? First of all, you need to have the sun in your back, and you need to look in this direction. So what happens in that case is that light is hitting, for example, droplets of water. Okay, and white light, it's basically formed by the addition of the different colors. And another interesting fact is that the light, it bends differently depending on the color of the light. So that's why you observe the rainbow, because the light, which is basically a superposition of all the colors, it's white, it enters from the air into the water, and then the light is bent differently. So for example, here we have the red light, and here we have the violet light, right? So notice that the violet light is bent the most, okay? Then here we have some reflection, right? So they cross here, and then from the water into the air again, another deflection, right? And that's why you can observe in this case the rainbow, because again, refraction, because the light bends differently depending on the color, okay? And this is not the only place where you can look at this rainbow. You can create your rainbow also at home. So for example, if you have doors or some glass, for example, you can make, for example, a tiny beam of light, hit that one, and you will observe, for example, this decomposition of light. So this phenomenon is called dispersion of light, okay? So, so that's another event, or another physical event where you can observe the physics behind it, right? So it's beautiful, but I think it's more beautiful when you understand what is going on, okay? Good. Okay, and now let's go to total internal reflection. What is total internal reflection? Something that we have said is that when light goes from one medium to another, basically the light, when it's transmitted to the second medium, is going to be bent. That doesn't happen all the time. So when you move, for example, when light moves from a medium with a less velocity of light to a medium with a larger one, you can find an angle theta in which the light is basically trapped in the first medium. And that trapping of the light into the first medium, that's what we call total internal reflection, right? And where we can observe this phenomenon, for example, in fiber optics. So what in this picture, what you have is a guy that is holding fiber optics, which is basically glass or plastic. And basically what you can do is you can convey information using light. And what is faster, light or electrons? Light, okay? So notice that that's why, for example, if you want to have a faster internet, your option is fiber optics, because all the communication is through light, okay? And here, for example, you have what happens, right? So here you have the pulse of light entering the fiber optics, and it's basically trapped inside the fiber optics, and it doesn't matter if you bend it, if you bend or twist the fiber as this guy is doing, the light is just conveyed anywhere, right? In terms of health, for example, laparoscopy, for example, it takes advantage of fiber optics. So the way in which the surgeon, for example, can enter your body without being ripped apart, for example, is just a tiny hole. And what they are doing is they are inserting the instruments and a camera. And the camera is basically sending or getting image, and that information is conveyed through the computers using fiber optics, right? So again, maybe you use your really high speed for gaming, for example, but notice there is physics behind that speed in the internet that you have. Okay, okay, cool. Now, what I want to show you is an experiment using a laser. Hopefully it will work, where I can show you here in this room how total internal reflection works. So here is the, can you connect this one? Huh? So this one. Ah, see here. Okay, so what we have here is a green laser, so I'm going to orient it that way so you do not, so I don't mess up with your eyes. Okay. And I don't know if we could turn off the lights. This one, I want to turn this one out. And let me see if I can make the camera in here, right? So notice that here what we have is precisely okay. Okay, maybe a little bit there. There, for example. So I don't know if you can more or less see. So maybe if I look from the top. Maybe I should have choose the red one. But notice that in this case, what I can do is I can basically trap the light in the interior of the water. Okay. Maybe if you approach, you would see better. Yeah, maybe I don't have a red one. Yes, it's in the lab.
And maybe we didn't.
Okay, so notice that in this case, what I have here, it's the laser, and notice that here what you have is precisely this light that is traveling into the water, and here the beam is hitting the water at this point, and it's bent back here, right? And how do I know that there is no transmission? Because notice that the point is more or less around here, and notice that I don't have any green spot in here, right? So that means that there is no transmission of the green light from the water into the air. So all the light is trapped inside inside the water. So in this case, I have a homemade fiber optics, if you will. Because of course, if we extend this, for example, all the 1 kilometer, for example, what is going to happen is that the light is going to be bouncing back and forth, and it's going to be transmitted, let's say, from this position all the way you want, okay? So that's how fiber optics works, okay? Okay. Okay. So you need to click in the presentation, Diego, please. Okay, there, okay. Okay, and the last topic that I would like to discuss is cars when they are moving in a circular path, right? And more specifically, so notice that if you have experience driving, when you enter a curve, usually you see a maximum velocity. It could be 90 kilometers per hour, 90 kilometers per hour, whatever, right? But notice the question that I'm posing here. So why is this maximum speed the same for all cars? So intuition, what does it tell you? That if you have a tiny car or if you have a heavy truck, which one has the largest possibility to flip over? And for example, so you should imagine that if a heavy truck goes faster, it's going to be easier to go down, right? And maybe a tiny car is not that problematic. So in that sense, what you should expect, for example, it's that these things said trucks circulate at this lower velocity, cars maybe circulate at 80 kilometers per hour, right? But what happens is that it doesn't matter, right? So it says everyone circulates at this maximum speed and you will be safe, right? And what I want to do is I want to tell you or explain a little bit why this happens, right? So I'm going to use really quickly some concepts that I'm going to use that you might be familiar with, right? So this one is famous, right? Force is equals to mass times acceleration, right? But how do we read this formula? We read this formula in the following fashion. If you have a massive object, an object with a mass, and if you exert a force on this object, this force is going to generate an acceleration on that object. So notice in this formula, what is generated on the object is the acceleration, and what is the agent that is producing that acceleration? The force. We write it this fashion because it's simpler, but the physics behind this, that this guy is the agent that is producing the acceleration, and what is the acceleration that is produced is given through this expression that you have here, right? Now, what happens when you have an object that is moving in a circular path? Whenever you have an object that is moving in a circular path, that object is accelerated, right? And the acceleration, it's called the centripetal acceleration, which is an acceleration that it's pointing, that is seeking always the center of the circular path. And the way in which you can calculate that acceleration is basically by knowing what is the linear speed of the object, and you need to know what is the radius of the circular path that you have, okay? And in that sense, for example, notice that if we replace this expression in this equation, what we're gonna have is this equation, right? So in this case, the force that you have here is going to be called centripetal acceleration because it's the force that is going to produce what? The centripetal acceleration that you have, okay? So what happens when you apply this to cars? For example, here you have the car that is, in this case, it's traveling with a velocity v in this direction. And what you're gonna have in this case, the centripetal acceleration is going to be the force of friction. So the force of friction is this force that you have whenever you have contact between two objects. And actually you can walk, or we can walk, because of the friction between your shoes and the ground, for example. So it's the same idea, right? So in this case, when your car is traveling in this direction, what you're gonna have is a force of friction between the tires of your car and the road. And in this case, for example, notice that what you're gonna have here is something that is called a normal force, which is a reaction force. And this normal force in this particular case is going to be equal to the weight of this object, right? And notice that in this case, the force that is pointing towards the center of this circular path is precisely the force of friction. So in this case, what is the force that is keeping you inside the road when you are driving and taking a turn? The force of friction, if you don't have an inclination in the road, right? And the force of friction is precisely proportional to the weight of the object, right? So here, for example, you might have the higher, the larger the mass of the object, the higher the friction, so the higher the acceleration, so you need to change the velocity. But notice what happens when we replace this expression in Newton's second law. So the centripetal force, which in this case is friction, is equal to the mass times the centripetal acceleration. And notice that in this case, if you clear this expression for the velocity, what you're gonna get is this division, right? So this mu that you have here, it's the coefficient of friction of the tires on the road, and it's constant, right? And the producers of tires, they know very well what is that one, right? And what's the thing that happens in here? So notice that you can cancel out the mass. And this mass that you have here is the mass of the object that is taking the turn. So notice that at the end of the day, the velocity depends on the mass of the object? Not at all. And this is the reason why, it doesn't matter what is the mass of the object that is taking the turn. What is the thing that matters? The acceleration due to gravity. What else? The radius of the circular path and the coefficient of friction. So what are the things that the people that is designing roads can control? They can control the radius, and they can control the mu. So if we know these parameters, then you can calculate what is the maximum velocity at which you should be driving to keep you on the road. So if you travel at a higher velocity than this one, what is going to happen is that friction will not be enough to keep you following this straight path. So that's why you need to slow down a little bit when you're taking a turn, if you don't want to get out of the road, right? But this is the physics. This is the physics behind taking a turn, for example, in cars. And of course, you can apply the same idea with some tweaks. For example, for racing cars. So when you have racing cars, what you have is that the road, instead of being a flat surface, what you have is a bank. So you have an inclination in there. So again, you can calculate, for example, what are the forces that you need to keep the car on the circular path, and you can calculate what is the velocity needed to enter that banked car. Because in that case, if the velocity is smaller, what is going to happen? The car is going to slip. If the car is driving too fast, it's going to go out of the road, right? And well, I think that's it, guys. So these are the examples that I have prepared for you. And I hope I convinced you that you will find physics everywhere, everywhere. You will find it in chemistry, biology, everywhere. I think that the only place where you cannot find it is in mathematics, but they are kind of like related, so. Okay. Huh? Yes, you do. Okay, so that's it, guys.
So, Dr. Velasquez, this was a really fun and amazing talk. We have a small gift for part of the committee and our sponsors.
Thank you.
Is there any question for Dr. Velasquez today? If anyone has any question? We remind you that we have the tickets for the raffle that we are going to announce the winners later today. So we encourage you all to ask questions. Okay, so
Huh?
Dr. Velasquez, Okay, now I get that fiber optics are better for transmitting information because light travels faster than the electrons.
Uh-huh.
But how do you manage to do or put that information like on the fiber optics, or how does information travel like as a form of light?
I am not an expert, so most probably what I'm going to do, I'm going to tell you is wrong, but basically what you do is you send pulses of light. And why do we do that? Because basically what we are doing is coding the information into zeros and ones. And that's what computers and other receivers, they can interpret as this information. So basically what I understand is that that's what you do. So for example, you can encode the letter A is this series of pulses. So when you send, for example, that information, that's how you do it.
So
So yes, it's not a continuous beam,
oh, perfect.
as far as I know. As far as I know. But again, I'm not an expert. So most probably what I told is incorrect, but
So hi,
Hi.
I just wanted to know in the Magnus effect, how does air pressure or humidity affect like the strength of the Magnus effect in the ball or in a moving object?
The Magnus effect, I didn't show the equations, but the Magnus effect depends on the spin. So the larger the spin, the larger the Magnus effect, the more intense the Magnus effect you will observe. Because if you recall in the first video, at the very beginning, so you have two contributions. You have the contribution of the velocity of the fluid and the spin. So in the first video where we saw the basketball falling down, so if you notice at the very beginning, the event was not that impressive. Why? Because at the very beginning, the speed of the ball falling down was not that large. But as if you recall, when you have an object falling into the action of gravity, the velocity increases, the magnitude of the velocity increases. And if you notice, the bending start to be evident precisely when the velocity of the ball was larger. That's because the Magnus effect is proportional precisely to the velocity of the fluid and the spin. So for example, in soccer, if you want to actually bend the ball, what you need to do is to give a really large spin to the ball, because if the ball is just spinning really, really small, basically you will not observe the curl of the curve. So that's why Roberto Carlos was impressive, because he was able, of course, he has a cannon in his left foot, but also he used a lot of spinning in the ball, and that's why you clearly see a really strong bend in the ball. So basically, if you want to strengthen the Magnus effect, what you need to do is either to increase the velocity of the fluid or the spinning, or a combination of both of them. Okay.
Any more question? No? Well, then, all of you, thanks for a lot to be joining us today. We have at 11 our second talk of the day with Daniela Camacho, which is called Woman of Soil. So we invite you to stay in the auditorium or come back at 11. Thanks a lot. And let's give Dr. Velasquez another round of applause.
Thank you. Este estuvo bien chido. Ese estuvo bien chido, este me gustó. ¿Sí? Pues a mí me gustaron. Hola, Lili. Pues hizo lo que se pudo.
No, no estuve para ver la que habías dicho del sunset.
¿no?
Sí,
Sí, es el de la monedita. Sí, y según yo se veía más chido con el láser verde. Sí. Vamos a guardar. Ay, cabrón, creo que lo guardé mal.
Ah, ok, ya lo estamos descargando.
¿Mandé? Ah, sí, sí, está bien, está bien, está bien. Esto va aquí. Este va acá. Ey,
¿Tienes familia?